Okie doke, we are having fun with Gauss's law now. We're going to do one more today, and this is going to be kind of like the last one, only totally different. Okay, what I have here is a cylinder, and so I'm going to try. Oh no, that sucks. Oh, that's a bad word. Let me try again. I'm going to draw the cylinder with cool 3D perspective, going in away from you, and it is like that. Okay, it's a solid cylinder, all right, and it has, oh, I don't know, radius. What shall I call it? I'll call it big R. And shall I make it infinitely long? I shall. Okay, so this thing actually goes forever. So it's kind of like a line of charge, except it's a cylinder. And here's what's interesting about it, is that it is made of plastic. It's made of an insulator. And I will tell you very quickly right now, we're going to get into this in another day or two, as I said in the last video. The reason it's important to say it's an insulator is that if it were a conductor, if this were made of metal, then all the charge would very quickly migrate to the outside surface. You can't have there be charge stuffed into the middle of a metallic solid. And we'll prove that using Gauss's law shortly. So not in this video, but this is an insulator. This is made of plastic. It's a long plastic cylinder. And in the last video, we had a sphere that was an insulator, and it had charge distributed uniformly throughout. This has charge distributed throughout, but not uniformly. And so this has actually a volume charge density, rho, which varies as a function of r, and it is equal to A times R. No, A is a bad constant. Scratch that, no A, because we use A for area. But not going to use K. C, generic constant C times R. Okay. And so what does that mean? It means that there's more charge, and I'm actually going to get rid of this picture, because I really want to look at this in detail. And so I want to make the cylinder bigger. There we go. That's a cylinder. And it goes on forever. I'm drawing kind of just a section of it here. Here's my radius R. And so what it means is that if I were to take a scoop of plastic from out here towards the edge, I'd get a lot of charge. If I took an equal-sized scoop in towards the middle, how do I get my scooper in there? I have no idea. If I were to take an equal-sized chunk of charge from the middle, it would have less charge. Lots of charge, less charge. And because the volume charge density is an increasing function of R. In fact, the very, very center, in the very, very middle, there is no charge at the very central point at all, because rho goes to 0. Okay, that's the meaning of that. What's the meaning of that? Uh-oh, didn't mean to do that. Ah! Get rid of that, get rid of that, get rid of this, all this stuff. Go away, and get rid of all that junk. Okay. All right. There's my radius. Okay. So what am I going to do? I am going to ask for the electric field. I'm going to say a point P, which is within, point P is over here, which is within this cylinder. Oh, this is going to be fun. All right. So what is the electric field? What is E at P? All right. By the way, you can, if you want to, you can make the sub pause this and see if you can figure it out and discuss and do crazy things like that. And then if you end up running out of time, then watch this later. Because you have to watch this because it's cool, and I expect you to know it. So, how am I going to do this? I think I'll start by drawing a Gaussian surface. And I will define what it is and where it is. And you notice this thing has this, this thing's a cylinder, it has this radial symmetry. And so I'm going to make the Gaussian surface. You may not be shocked to know that this will be a cylinder. And I want this point P to be on the curved wall of the cylinder. My picture's not very good here. I'm going to move my point P kind of inward, and I'm going to draw the axis of the cylinder. So here's the axis of the cylinder. And so point P is a distance little r from the axis of the cylinder. All right, and it is big R, of course, to the outside wall of the cylinder. So little r is where P is, and little r is less than big R because it's inside the cylinder. All right, so now I'm ready to draw my Gaussian surface. My Gaussian surface will be a cylinder, and I want point P to be on the wall of this cylinder. So here is my Gaussian surface. That's not too bad. Of mixing colors here, radius little r and length h. So this is h from here to here, and it is coaxial with big cylinder. All right. Okay, so I've defined my Gaussian surface with point P on the curved wall edge. Now I'm going to find the flux through the Gaussian surface. And the electric field is everywhere radial for the same symmetry arguments that we've made in the past. Boy, this is a terrible 3D picture, I'm just realizing. We're going to have to live with it. So the electric field is everywhere radial away. So if I were to draw some electric field vectors on the wall of the cylinder where point P is, the electric field points straight away from the axis. And that, of course, is parallel to the dA vector at that point as well, because it points straight out of the Gaussian surface. There's my dA vector. There's my E vector. Okay, the total flux through this Gaussian surface. This is step 2. Step 1 is define the what and the where of the Gaussian surface. Step 2 is what is the flux. And the flux, in this case, this is the same with the linear charge distribution we did earlier. We have 3 parts of this Gaussian surface. We have the wall plus 2 end caps. Okay, the end caps are because this Gaussian surface is not a toilet paper tube. It is a orange juice can with solid ends, even though they're not solid because it's a Gaussian surface. It's imaginary, but so it has caps. It's got walls. It's got ends. Okay. How much flux goes through those caps? None, because E everywhere on these caps is radially out, but the dA vector is axial, parallel to the axis. And so for the caps, everywhere on the caps, E is everywhere perpendicular to dA, everywhere on those caps. And so since flux is the dot product, the flux through the cap is dot product of E dot dA. It's 0 because the dot product of 2 perpendicular vectors is 0. So there's no flux through the cap. So we're left with the flux through the wall of the cylinder. And the wall, this is identical to the problem we did earlier with the infinite line of charge. What's going to be different here, clearly, I think, is when we get to the Q enclosed part. So the flux through the wall is surface integral E dot dA, vector, vector. But we now have the 2 things we get to say. One is that E is everywhere parallel to dA. So I will say it every time. E is parallel to dA. Everywhere in the world on the curved wall of the Gaussian surface. So that means that the dot product cosine phi gets arrow 1. So the dot product becomes just E times dA. And then I have E uniform in magnitude everywhere. Notice I didn't vector that symbol. E, the magnitude is E uniform everywhere. So now I'm going to move over here because I need room. The integral becomes, E comes out as a constant, integral dA, and that's of course just area, so it becomes E times A. Integral of dA is all the area added up, it's just E times A. Okay, that's the flux through the whole thing is the flux through the wall plus a couple of zeros for the flux through the end caps, and it's just E times A, where this A is the area of the wall of the cylinder. So let's actually do that sub right now. E times the area of the wall of the cylinder is 2 pi little r times h. Okay. Now we finally write Gauss's law, and Gauss's law says the total flux is Q enclosed over epsilon naught. We have this stuff here for the total flux. It's going to plug in for total flux. E times 2 pi RH. Is Q enclosed here? That's a bit of an issue, and this is a big issue. How much charge is inside my Gaussian surface? What is Q enclosed? Well, I want to say, I'm going to have to work down here, I want to say that Q enclosed is equal to rho times volume, but rho isn't uniform throughout the volume inside the Gaussian surface. I will write here, this is the volume within the Gaussian surface. Gee, how do I multiply two numbers when one of them is varying throughout the other? Integrate, integrate, that's the music. So what I have to do now is divide this cylinder, this Gaussian surface. In fact, I'm going to redraw this farther down so we can look at it instead of swooping back and forth. Here's the Gaussian surface. It is a cylinder, and it has radius little r and length h. Okay, what is the charge enclosed within the cylinder? Well, what I want to do to integrate this, remembering that rho is a radial function, it is, what do we call it, c times r, it increases with radius. So what I want to do is divide this up into pieces, each of which has uniform rho. To have uniform rho, each piece has to have a uniform little r radius. I have to be very careful here with my r's. My Gaussian surface has a fixed r, which I'm going to call, I'm going to just rewrite this as the r subscript g for the radius of the Gaussian surface, because I'm going to be interested in the charge of bits of stuff within this thing of smaller r's than that. So this is going to be a variable, whereas this is a, for the purposes of this particular problem, this is a constant. Okay, that's how far point P is away from the radius of the whole thing, r subscript P for Gaussian surface. Okay, okay. So how do I break this solid plastic stuff within the Gaussian surface into pieces of constant radius? I know it says variable because each piece will have different radius, but so it'd be like, what is the locus of points that are all distance little r away from the center? Well, what I'm going to get here is a shell. Key word here is shell. All right. Oh, that's a terrible. I know my art is bad, but that was awful. Okay, what I'm going to do is, now is where we're talking toilet paper tubes. Earlier we weren't. Now we're talking toilet paper tubes, because what I'm going to do is divide this into coaxial toilet paper tubes of varying radius. I'm going to call this radius r, little r with no subscript. That's a variable. And let's examine this toilet paper tube a little more closely because it has thickness. All right, so I'm going to draw this toilet paper tube, and it has thickness. It's the thickness of the cardboard, if you will. And this is one of these shells. And what is the thickness of the cardboard, this imaginary cardboard of this toilet paper tube? Why, golly, it's dr. And what is the radius of this shell? It's little r. And what is the length of this toilet paper tube? It is h. Okay, how much charge does that toilet paper tube have, that shell, of which there are a zillion within my Gaussian surface? Well, the charge of that shell is dq, because it's an incredibly tiny amount of stuff since it's so wafer thin. And this is going to be equal to rho, because this is the beauty. The volume charge density varies with radius, and for this particular toilet paper tube, every bit of stuff, plastic, cardboard, has the same rho because it's all the same distance away from the center. So it's constant for this, and so the charge in this thing is rho times the volume of cardboard in my toilet paper tube. What is the volume of cardboard in this toilet paper tube? Well, what is the shape of this toilet paper tube? Well, clearly it's a rectangular solid, because if I make a cut down here, we've done the same thing with rings before. if I make a cut down there, I can flatten this thing out. And I'm going to make a cut, and I'm going to open this thing up, and it turns into a rectangular solid when I unroll it and flatten it out, and it's very thin. Okay, this is after I've flattened out this roll, and because it's so thin I can flatten it out and it doesn't crinkle anywhere. Okay, what is this thing? Well, this is a rectangular solid of height h. That's this height here when I straighten it out. This dimension is the circumference around this toilet paper tube, so that's 2 pi r. And the thickness of this thing is dr. So the volume of this, 2 pi r down here, the volume of this solid, dv, so I'm going to rewrite this, this is very neat and tidy, dq is equal to rho times dv, and dv is length times width times height. I may not have named those correctly, but it's those three things multiplied together, which is 2 pi r times h times dr. Phew! That is dq. That's the amount of charge in one of these toilet paper tubes. There's a lot of them. And we have to find remember what we're doing here. We're finding Q enclosed. And so we have to, which we can't do by straight multiplication. We have to integrate. And so I have to work back over here. So Q enclosed is the integral, all these dq's added up of dq, but dq itself is that big mess down here. It is rho. Oh, but what's rho? Rho's not constant. That's kind of the whole point. Rho is this, what do we call it? C was a constant? All the way back up. C times R. Rho is C times R. C times R. So I'm just subbing in for this rho here. Times 2 pi r h dr. Oh, golly, there's a couple of r's there. So I will simplify this again. 2 pi, I feel like pulling that out, c r squared h dr. Okay, that's dq. So that's what I have to integrate. So I'm going to plug that in. 2 pi c, I'm going to say h r squared for reasons that should be clear, because now I have all my constants. This is q enclosed. Now I have a whole bunch of constants. From the 2 to the pi to the c to the h, those are all constants. They all come out. And so q enclosed is 2 pi c h integral r squared dr, and I'm going to integrate from 0 to r of the Gaussian surface. Little r, not big R, the whole thing. And so this is going to be integral, I'll write it, integral r squared dr from 0 to rg. Q enclosed equals 2 pi c h, having fun now. Integral of r squared dr is r to the cube, that's good, over 3, integrated from 0 to rg. And so I end up with 2 pi c h. I've got an over 3, and I've got an rg cubed minus 0 cubed. I'm not going to write that down because I'm lazy. So that's the Q enclosed. Boy, I hope that's right. And so now, am I ready to actually find the field of point P? Holy Stromboli, where are we up here? Here's my, the last time I wrote Gauss's law. Flux equals Q enclosed or epsilon naught. Down there I have an expression for Q enclosed. I have here an expression for flux. I'm ready to start plugging things in and pray to goodness that everything falls out. Let's see. So flux equals Q enclosed or epsilon naught. Let me start down here. Flux, a new color, equals Q enclosed over epsilon naught. Flux is, where'd it go? E2 pi RH. E2 pi RH equals Q enclosed. I got that around here somewhere. Here's Q enclosed. Equals 2/3 pi CH R of the Gaussian surface, which is what this one is over here as well on the left. I just put a little substitute G there. Cubed over epsilon naught. Boy, it looks like a lot of stuff is going to cancel. Let's see, let's start with easy stuff. The low fruit, 2, gone. Pi, gone. RG, one of them gone, that's now squared. H, gone. Cool. E equals, I think we have it, people. We've got a 3 epsilon naught on the bottom. I've got a C times R, which is the Gaussian surface, but that's where point P is. On top, I think we're done. Boy, I hope that's right. If there was a mistake early on that I carried through the whole thing, then I'm embarrassed. I'll just say right now, how do I make sure this is right? I make sure this is right by making sure the units work out. And the way I make sure the units work out is by going back and figuring out what the frig the units are for big C. The units for big C, rho is coulombs per meters cubed. R is meters. Okay, so C, by the way, the C is in coulombs, of course. That maybe wasn't a very good choice for the name for the constant. C has to be coulombs over meters to the 4th, right? Because now that's an equality. So C has units of coulombs per meters to the 4th. So as that work down here, that means that this is going to give me, I should say, I leave this as an exercise. I have to do this in a different color. I'm going to put the units in for everything. Coulombs over meters to the 4th times meters over epsilon naught, which has units of parents per meter, but it's not. It's the inverse of units for K, which is Coulomb squared, Newton meter squared per Coulomb squared, per Newton meter squared. Boy, is this actually going to work? And I'm looking for newtons per Coulomb. Oh boy, something's bad because the units don't work out. Oh boy. Meters. This is meters cubed. These come upstairs, so I have that's not cubed. That's cubed. This is and got too many meters. Well, this is embarrassing because the units don't work out unless it. So okay, here's what I'm going to say. Find my mistake. I dare you. Bet you can't. I think the approach is right. I think I made a screw up somewhere. Somewhere I made a screw up because those units don't agree. I have too many meters left over. Extra credit for finding my mistake. Ha! Good. See ya. Bye. Bye.